Okay, like I said, this is a very important chapter. Uh, Oscillations. We'll study the most fundamental kind of oscillation. Okay. What is an oscillation? An oscillation is any kind of repeating motion. Okay. And if you, well, as an engineer, this will never leave you. Anytime you study any vibrating system, you'll come back to this, the basics. Okay. So let me show you oscillating system that we will talk about mostly. Right. And this is, so here's the mass attached to a spring. And let's make sure gravity none. And spring constant, no damping. Okay, so damping is 0. So this is the basic oscillation we'll study. Okay. This is called a simple harmonic motion. Okay. And for something to oscillate, here's what you need. Okay. So let's say here's the system, here's the equilibrium state of the system. Okay. So if I pull down, let's go here, no gravity, forces, spring force. Okay. So here's what you need basically for a oscillating system. Okay, so we are dealing with no gravity. Okay, no gravity, meaning we are doing this experiment, let's say in space, in the International Space Station. Okay. So the only force that's acting on this object, on this mass, is the spring force. Okay. So there's the equilibrium position. And look at this. If I pull it in this direction, that blue arrow is trying to bring it back. Okay. If I push it like that, what is the spring trying to do? Bring it back to the equilibrium position. So that is called a restoring force. Okay? So when you have a restoring force, you'll have oscillations. Okay? So for instance, let me give you a counterexample. So let's say you have a marble on top of a hill. You disturb it, the force of gravity will pull it away, not bring it back to the equilibrium position. Okay? Here, the force of gravity will pull it away and not bring it back to the equilibrium position. On the other hand, if you're in a valley, okay, the same force of gravity is a restoring force now. Okay? So for something to oscillate, what you need is a restoring force. Okay? Now this entire chapter is about a special kind of restoring force. Okay? So here's the spring, here's the mass attached to the spring, and here's the equilibrium position. We'll denote it by x naught. Okay? So if I pull the mass to here, the restoring force is in this direction. Okay? And if I push the mass here, the restoring force is in that direction. Okay? The force is in this direction. Now the special thing about this force is, if the displacement is x, the restoring force is proportional to the displacement. And that's what we're studying. Okay? This will lead to simple harmonic motion. Okay? It's not kx squared, it's not kx cubed, it's not kx to the power half. Okay? The minus sign just tells you that when x is positive, the force is in the negative direction. And when x is negative, so this is your origin, when x is negative, negative times negative is positive. The force is in the positive direction. Okay, so this entire chapter, we're studying systems where if you disturb the system from its equilibrium position, the forces that come into play are restoring it to the equilibrium position. Yeah? And the second thing that's special is the restoring force is proportional to the disturbance. Yeah? So that's what we're studying. You guys understand? Okay, so so for instance, if the restoring force was F equal to minus kx squared, that would be a very hard problem to study. Okay? And we're not going to do that. All right. So oscillations is what we're studying. All right. So here's and keep this in mind. So again, we are dealing with no gravity. I mean, we want to keep things simple. And here's the oscillating system. Okay. This is one oscillation. So if you start from one extreme point, go to the other extreme and come back, that's one extreme point. That's one oscillation. The time for one oscillation is called a period. Okay? All right. Now let me see. Okay. So here's this oscillation. Let's say this took 2 seconds to complete one oscillation. I'm just making up the number. Here's the same system. What is the difference? The amplitude of oscillation is greater now. You think this took longer time? Yes? No? It's covering a longer distance. So, for a simple harmonic oscillator, as long as you learn this, as long as the restoring force is proportional to the displacement, the period is independent of the amplitude. Okay? All right. So those are some of the properties we'll study. All right, so here's your system now. So this mass is sitting on a frictionless system. And you see, there's the equilibrium position. You disturb it from the equilibrium position, the spring exerts a restoring force. If you compress the mass, if you compress the spring exerts a restoring force. Okay? Now here's another feature that's common about oscillations. And let me go back to that simulation. Okay, so we'll look at energy. So again, gravity none, damping none. What is damping? Friction. Very good. Okay. So, all right. So for something to oscillate, we'll make it. Okay. So what needs to be true is you need to have two forms of energy, and the energy is oscillating from one form to another. Okay. So in this case, this has kinetic energy and spring potential energy. Okay. So right now, all of the energy is in potential energy. Then it gets converted to kinetic energy, back to potential energy, and so on. Okay. So for a system to oscillate, you need to have two forms of energy, and the energy oscillates back and forth. At least two different forms of energy. You can have more than two forms. Okay. So for instance, we can put gravity in, and now you can have gravitational potential energy as well. So you have three forms of energy. Okay. And as long as damping is not present, as long as friction is not present, here's the total energy. What is happening to the total energy?
Conserved.
It's constant, it's conserved. And so how long will this oscillate? Forever. Okay? All right, so now you know the basic features of what we're studying. Okay? All right, so again, we have periodic motion, meaning the motion repeats itself every period. Okay? What we are studying is a simple harmonic motion, and the motion is simple harmonic when the when the restoring force is proportional to the displacement. And simple harmonic motion, you can give the position of the particle as a cosine or sine function. Okay, that's a simple harmonic motion. All right. Now here's the next thing you'll study. Let's make sure we understand this. How many of you guys are taking differential equation? Okay. So you'll all take differential equations. Okay. And here's one of the reasons you'll take differential equations. Okay, so let's make sure we understand this. So here's a system that you want to study. When you want to study this, what is it that you want to know? Let's say if you disturb the system, or you put in certain amount of energy in the system, you want to see how the system will evolve. What you want to know is what will the position of this mass be as a function of time. Okay, so this is giving you the configuration of the system as a function of time, meaning how it will evolve. So for instance, you might want to hit this table with a hammer, and how will the table behave? Okay. You might want to light a fire in the corner of the room, and how does the heat spread? Okay. So you want to study a system and how it'll evolve in time. Okay. So what you want to do is study a system, okay, and then its evolution in time. All right, there's two things you can do. You can set this up in lab and try and make measurements and study it. Okay? And that can get a little messy and a little troublesome. Or what you can do is you can come up with a mathematical model for this system. Okay? What do I mean by a mathematical model? We come up with an equation that this function must satisfy. Okay? So that's a mathematical model. And more often than not, that mathematical model will be a differential equation. Okay? So here's how it will work. You guys following this? Okay. So you have your system that you want to study. Okay? So you put in a physics principle to come up with the mathematical model. Okay? All right, the physics principle here will put us very simple. We'll put Newton's second law. That's the physics that will go. What is Newton's second law? I'm sorry? Yeah. The force acting on a mass is equal to mass times the acceleration. Okay? What was the force on this guy? It's minus kx. Okay? So the force is minus kx. Okay, wherever that object is, that's the force on it. And its acceleration is given by, acceleration is second derivative of time. So what do we have? What is this equation? No matter what this guy does, his position as a function of time must satisfy this differential equation. Okay? So all we did was put Newton's second law in and got a equation, your mathematical model, that governs the behavior of this guy. So if you want to study this, you can either set it up in lab or just learn to solve this differential equation. Okay? And that's what you like to do. Okay? This is very easy to do. And that's what you want to do. Okay? So again, let me summarize this process again. You have a system you want to study. You put in some physical principle. Physics law, generally it's a physics law. Okay? You put in the law, the physics law that governs the behavior of the system, and you'll get an equation, a mathematical model for the behavior of the system. And then you learn how to solve this differential equation. Okay. So that's why you study differential equations. You'll study to solve various kinds of equations that'll show up in the study of a whole bunch of systems that you study. Okay. All right, any questions at this point? All right, so there's the equation. So dx squared, I'll divide by m, so minus k over m. What is k? Spring constant. Is that a positive or a negative quantity? I'm sorry? That's always a positive quantity. Okay, the spring constant is always. How about the mass? It's always a positive quantity. Okay, so k by m is always positive. Okay, so just to make sure that there's no confusion, we write it as omega squared. Okay, this guy is always positive, so that's why we just write it as omega squared. Okay, so d square x by dt square is minus omega square times x. Okay, we'll bring that over here, and so here is your equation. Okay, so xt, what is xt? Xt is the position of this guy as a function of time. Okay, whatever you can do, you can come and kick it, and that'll be one solution. That will be one motion. You can hit it with a hammer, that'll be another solution. Okay, but all those solutions, all those motions need to satisfy this differential equation. Okay, so that was our goal. The behavior of this system is modeled by this equation. What is it that you're ultimately interested in? I'm sorry?
Position of the function.
That's right. You want this guy. This is what you're interested in. So now it's a matter of finding out what functions satisfy this equation. Okay? And that's what you'll learn in differential equation. Because you learn, so it's a little guesswork, it's art and science. Okay? So you try various solutions. Okay? And you learn to bark up the right trees. Okay? So here's a solution. Somebody pulled it out of their hat. Yep. How do we know that if that's a solution? Well, plug it in there. Check and see if it satisfies it. All right, so let's do that. Okay. So what we are saying is, okay, xt, the position of the mass attached to the spring satisfies this differential equation. And what we are saying is xt is equal to a cosine omega t plus phi. You know what omega is? Omega is k over m. All right? So now here's a general feature. Okay. Look at this in the solution. There's this a, and there's this phi. See, these guys are nowhere in the equation. Omega square is in the equation. Okay, so here's a general equation, a general feature of this differential equation. If it's a second order differential equation, you'll get two constants that come in the solution. Those will have to be determined by initial conditions. Okay, what we mean by initial conditions, so here's an example of initial condition. X naught, what is the value of x naught? Okay, and that's one initial condition. And then you can have x dot naught, or x dot meaning that's the velocity. Velocity is a function at time to equal to 0. Okay, so that'll be one constant, that will be the second constant. Did you guys understand that?
So because it's a second order derivative, we're allowed to have two constants.
Two constants will show up in the equation.
Yeah, okay.
So if it was a third order differential equation, how many constants will show up in the solution? 3. If it was fifth order differential equation, 5 constants we should. Okay? Now, okay, so this is a second order. It's called a linear differential equation. Okay, this would be a nonlinear differential equation. Okay, this will be a nonlinear differential equation. Okay, each term is to the power 1. Okay, okay, so it's a second order linear differential equation. All right, what does that mean? If it's a linear differential equation, it doesn't matter what order it is. If x1t is a solution, x2t is a solution, then x1t plus x2t is also a solution. Okay? So for linear differential equations, that's true. Did you guys understand that? Okay. So for instance, if the equation was like this and this was a solution and this was a solution, this won't be a solution. Okay? This is all important. You gotta understand this, okay? You have to learn this stuff. All right, so, oops. Well, I need that. All right, so here was, see, so the x, this is the position of the mass attached to the spring, satisfies this differential equation. And we said that, I told you that somebody pulled out of their hat this solution, okay? Let's make sure that they were right, okay? So let's do this. So dx by dt derivative of cosine t is minus sine, okay? So minus a omega sine omega t plus phi. And then t square, what we need is the second derivative. We are calculating this term. Okay, help me out. What is the second derivative? So the derivative of sine is cosine, okay, and then you get an omega. So that's minus a omega square cosine omega t plus phi. Okay. I'm going to erase this because I need space. All right, so now let's substitute it. We have the second derivative, we'll put that in there. And then we have this function, we'll put it in there. Okay, so minus a omega square cosine omega t plus phi plus omega square times a cosine omega t plus phi. And that is identically 0. Okay, so this is indeed a solution. All right, now you've solved the problem. You know where that mass is going to be at all times. Okay, and you know everything there is to know about the problem now. Okay. All right, I know that was quite a bit of information, so let me review this again. Here's a system you want to study. What do you mean by wanting to study the system? Let's say you put some energy into the system. How does the system evolve? Meaning you want the position of the mass as a function of time. Okay. To be able to get that, what you do is you try and come up with a mathematical model for the system. And what is the mathematical model? The mathematical model generally is a differential equation. Okay? So you came up with a differential equation that described that describe the behavior that the system's configuration need to satisfy. So this differential equation described the behavior of the system. Okay? and then you learn how to solve this equation. Here's the solution. So no matter what you do to this guy, that position as a function of time is given by that. Okay, so that's it. All right, so as long as the restoring force is proportional to the displacement, what you get is a simple harmonic motion, meaning the position is given by a sine or a cosine function. Okay? And these two constants are determined by the initial conditions. Okay? And we'll see that. Okay, so for instance, let's say here's my initial condition. So there's the equilibrium position. What I'm going to do is I'm going to pull this mass to the side, okay, at a distance a, and let go of it. So what is its velocity at time 0? 0. Okay, so xt, here's the general solution, a cosine omega t plus phi. Okay, so at t equal to 0, this is at t equal to 0. At t equal to 0, this is 0. And you want x of 0 to be a. So that implies phi equal to 0. Okay, because when phi is 0, t equal to 0, cosine of 0 is 1, and x of 0 will be a. Okay. Now let's do the velocity. Velocity is omega t. Remember, phi is 0. Okay, so at t equal to 0, velocity is sine of 0 is 0. So this would be 0. Okay. So if at initial condition you've set it at a was 0.1 meters, you pulled it at 0.1 meters and let go, that means it starts at velocity 0. Then your solution is, this solution is xt is 0.1 meters times cosine omega t. See, your initial conditions determine this constant and that constant. Okay? All right. Mm-hmm. All right, so here was the solution. Xt is a cosine omega t plus phi. Again, those are constants that are a and phi are determined by uniquely by position and velocity of the particle at t equal to 0. Okay, two initial conditions. So again, if we had an equation like this, I'm just showing you a different situation. Okay, how many constants will be there in the solution? 3, and you'll need 3 initial conditions. Okay, all right. So this guy, x is plotted as a function of time, and here is a cosine function, sine or cosine function. Okay. Well, you know where it is at all times. You take the derivative of it, you know the velocity at all times. You take the derivative of that, you know the acceleration of the particle at all times. Okay? And that's all you need That's all we generally want to know, and we're all set. Okay? Okay, so again, what was it? System, some physics principle, the mathematical model. We came up with a mathematical model, which is a differential equation and a solution. That's the way to study systems. Okay? And you'll be doing that for many, many systems. Okay, the system could be a predator-prey system. It could be a vat of chemicals reacting. Okay, it could be the stock market. It could be the weather. Okay, and the more complicated the system, the harder it is to solve the differential equation. Okay, the more complicated coupled systems you get. Okay, so that's the basic idea. So when they get the solution, what are they getting? X as a function of time. And this is what the weather is 3 days from now. I mean, this is a very simplified thing. Okay, at t equal to 3 days, what is the weather going to be like? You know? So that's the idea. All right, so what this is a physical demonstration. Okay, so what we are trying to show is, okay, this is all real. Okay, in the sense, okay, so what you can do is, so you can get this paper to move at a constant speed. You get this mass to oscillate, attach a pen there, and what you'll see is you'll get a sine or a cosine graph, showing you that this thing is physical. Yeah. All right, so next we want to become familiar with these two terms. Period is the time for one oscillation. Okay? And frequency is how many oscillations you do per second. Okay? And the period is given by 2 pi square root of m divided by the spring constant. And let's make sure this makes sense. Okay. So I'll show you. Let's go here. Okay, so you can see the oscillations there, right? Okay, what I'll do is I will, so the spring is the same. I attached a heavier mass. Now what happened to the oscillation? What happened to the period? I'm sorry? It's a longer period. Period increased, right? And that's what our formula is saying. See, when the mass increases, the period increases. Okay? What our formula also says is if the spring constant is larger, the period is smaller. Okay? So stiffer the spring, smaller the period. All right. There's something neat about this formula. Does anybody see that?
Angular frequency is the square root of m over k.
Right, right. Okay, so here's what I'm getting at. So here is one oscillation. How about for this oscillation? What is the period for this oscillation? So this is the amplitude. A1, A2. See, the amplitude doesn't come in the formula. The period is the same for this oscillation as it's for this oscillation. That's why those grandfather clocks are possible. You have a pendulum, and as the amplitude dies down, it's still keeping good time because the period is the same. Okay? All right. So frequency is inverse of the period. That tells you how many times it will oscillate per second. Okay. All right. So we've talked about 40 minutes, and this one slide summarizes everything. Okay. So you had a system. Here is the mathematical model for the system. Here is the solution. Okay. And now you know what the system will do at all times. Okay. So if you wanted the velocity, you just take derivative of the position. You want the acceleration, you take derivative of the velocity. What do these guys give you? See, here's the velocity. And the velocity, the only thing that's changing is the sine and cosine function, and the maximum value for the sine function is 1. Okay, so the maximum velocity, okay, so it's absolute value, the maximum value is 1, but it can be plus or minus 1. So the maximum speed is omega times a, okay, with this being 1. And the maximum magnitude of the maximum acceleration is a omega squared. Okay, that's what this is telling you. All right, so going back to this diagram. Okay, so let's say I pull this guy over here and let go. I pulled it there and let go. When will the speed be maximum?
At the equilibrium.
Very good. So the speed will be maximum here. When it's going in this direction, the velocity is positive. When it's going in this direction, the velocity is negative. But that's when the velocity will be maximum. Okay? So this is V max. When will the acceleration be maximum? When will this be true? Extreme points. See? Very good. So force is minus kx. Kx equal to mass times acceleration. Acceleration is greatest when the force is greatest, and the force is greatest at the extreme points. So acceleration is the greatest here. So when it's going there and coming back in this direction, acceleration is in that direction, maximum acceleration. Okay. So at the two extremal point, okay, here the acceleration is minus a omega square, and here it's plus a omega square. Okay. All right. So this one slide captures everything. Okay. All right. Do you have any questions so far? Okay. I don't want to give a break. I know it's a long chapter, but I want to keep continuing, okay? Because we're going to I'm recording this and now we said that when you have an oscillating system, you got to have at least two kinds of energy, okay? And when the system is oscillating, what is happening is one kind of energy is being converted to another and back and forth, okay? So when this thing oscillates, right now it has potential energy, here it has all kinetic energy, and then when it's fully compressed, it'll be all potential energy. And what you find is if you take the sum of kinetic and potential energy at every point, the sum of kinetic and potential energy is constant. Okay, so the total mechanical energy is constant for this motion. When is it true? When is that statement true? When there is no friction. Okay, so the sum of potential and kinetic energy is constant, and it's equal to what is this equal to? That's the maximum potential energy when it's at the extreme point. Okay. All right. Now, what does this formula give you? See, as this thing is oscillating, what is happening to the speed? It's getting faster, and the speed will be maximum when it's at the equilibrium position, and then it starts slowing down. Okay? So, at different positions, it has different speed. And this is giving you, so this is actually giving you the velocity bit because you can take the associated with the sign. It's giving you the velocity as a function of position. So let's make sure that this is true. At x equal to 0, the velocity will be maximum. It'll be, this is omega square, a square, so it'll be a omega. At x equal to the amplitude, at x equal to a, at the extremal points, the velocity is 0. Okay? So what this formula is giving you is the velocity as a function of position. Okay? If you know where your mass is located, you can calculate the velocity of the guy using this formula. All right, so let's go to, you guys see this guy. Here's a mass attached to a spring. This is what's called a torsion pendulum. Okay, you take a stiff metal wire, attach a disc to it, and now we'll look at another kind of oscillation. What we'll do is we'll twist it. Okay, so you twist it. If you twist it, there's a torque that the metal wire will apply, and it'll restore it. Okay, so you guys understand this motion? Okay. All right, let me ask you this. Is this motion and this motion, are they any way related? You think they might be related? They look very different, don't they? And you'll see in a second that the mathematical model, the differential equation describing the two motion is identical. Okay? So that's the amazing thing. Okay? So, all right. So for this system, how did you measure the configuration of the system? You measured the position of this guy as a function of time. Okay? So when you twist this guy, the way to measure the configuration of the system is to measure this angle as a function of time. Okay, or I mean, here it's max, they write maximum, but anyway, theta as a function of time. Okay, so instead of giving the position as a function of time, we'll give you the configuration of the system by measuring theta as a function of time. Okay. So when you twist it this way, the torques that this twisted wire applies, it tries to bring it back, and the restoring torque is proportional to the displacement. The more you twist it, the harder it'll try and bring it back. Okay. The greater will be the restoring torque. Okay, so it's tau minus kappa theta squared. And torque, Newton's second law is I times alpha. Alpha is angular acceleration, I times d squared theta by dt squared. All right, so this is dt squared. We'll divide by I. So d squared theta by dt squared is kappa by I. Kappa, the torsion constant, that's positive. I is the moment of inertia of this guy about that axis. That's positive. So since both are positive, we'll write that as omega squared. And then you bring that over here. Here's the differential equation satisfied by this system. Okay. Let me show you That's exactly this differential equation satisfied by this equation. Okay. So it was just a matter of the configuration of this guy was measured, this system was measured by xt. The configuration of this guy was measured by theta t. And that coordinate, both those coordinates satisfied the exact same differential equation. So here, the message, the take-home message is, you see, very different systems, apparently different looking systems, mathematically are equivalent. Yes, so the same differential equation satisfies the behavior of that system. And of course, now you're experts at differential equations. You know how to solve this. There's the solution. Okay. And again, here's a second order linear differential equation, and here are the two constants that were not in the original equation. And what will determine the two equations? Initial conditions. Yeah. Okay, so again, the period is given by kappa by I. Again, the angular frequency, and angular frequency for the mass attached to the spring was given by this. This was the spring constant divided by the mass. For something that's rotating, mass gets replaced by moment of inertia. The spring constant got replaced by torsion constant. Yeah. The period for the spring was given by 2 pi m by k, and again mass got replaced by moment of inertia, and k got replaced by kappa. Okay, so this guy and this guy, they're cousins. Okay, you wouldn't have thought of that before you saw the equations governing them. Okay. Now let me introduce the other two cousins. Yeah. You'll see that this guy, the behavior of this guy is also given by exactly the same differential equation. Okay, so here's a simple pendulum, and here's a physical pendulum. The behavior of this guy is also given by the same differential equation. So here are four very different looking systems, and they're mathematically modeled by the same differential equation. Okay, so whatever coordinate you put to measure the configuration of the system, okay? So it's the same differential equation, okay? All right, so let me run through that quickly. All right, so the simple pendulum, okay, so here's a mass, a heavy mass hanging by a thread. Okay, so when it's there is the force of gravity. There's only two forces acting on it, force of gravity and the tension in the string. This component of the force of gravity is balancing the tension, and this component of the force of gravity is the restoring force. It's bringing it back to the equilibrium position, okay? So that's the restoring force. So mg sine theta, this is mg sine theta, mg sine theta, okay, so mg sine theta equal to minus mg sine theta. S is increasing in this direction, is m d square s by dt square. S is this arc length. Okay. And the arc length is given by L theta. Theta is that. Okay. So if the angles are small, for small angles, and we mean small angles less than 0.1 radians generally, 0.1 radians is about 6 degrees. Okay, so for small oscillations, sine theta can be approximated by theta. And you can check this in your calculators. Put your calculator in radian mode and do sine theta, and for radians less than 0.1 degrees, sine theta will be almost equal to theta. Okay. So this will be mg theta. Okay. So let me do this. So for small angles, you can approximate that equal to m d square. L is constant. Okay, so if you measure the configuration of the system by this angle, the differential equation satisfied by this angle is this, which is exactly the same differential equation. So this, we'll call this G is positive, L is positive, we'll call this omega square. D square theta by dt square is plus omega square. D square theta okay, so this equation by now should be your best friend. Okay, so if you measure the configuration of the system by this angle, there's the differential equation. Okay, and you know how to solve this. Okay, you memorize the solution. Okay, there's the solution. So there's a constant that was not in the original equation. There's that constant again. Those two constants are determined by initial conditions. Okay. There's the formula for the period. The period of oscillation, the time for one oscillation, is 2 pi L. L is the length of the pendulum. The length of the pendulum is from the point of suspension to the center of mass of this mass hanging, divided by the acceleration due to gravity. So you see, you can use this to determine the acceleration due to gravity. You can use a simple pendulum to determine the acceleration due to gravity. I don't know if you guys have seen old movies of the Apollo landing. So one of the first things that the astronauts, when they landed on the moon, was they set a pendulum on motion on the lunar lander. So kids watching at home, they're watching on TV, they could measure the period of oscillation. They were told the length of the pendulum. And by measuring that, they could calculate the acceleration due to gravity on the moon. Okay, so that was the idea. So go check it out on YouTube. So this is called a simple pendulum. A simple pendulum is a small heavy mass hanging by a light string. Okay, so essentially, this is essentially a point mass, and all the mass is there at the length, at distance L. Okay, a physical pendulum is the mass is more distributed. Now, if you nail the thing at the center of mass, then this won't oscillate. But let's say you nail it over there, then if you disturb it, the center mass is disturbed from below this point of suspension, it'll oscillate. Okay, and again, we'll measure the configuration of the system by this angle. That angle is the point of suspension and the center of mass makes from the vertical. Okay. And when you disturb it, the restoring torque is, there's the weight times the moment arm. You're calculating the torque about this point. Okay, so here's the weight times the moment arm. When the center of mass is right there, right below it, the torque is 0, and when it's there, this is a clockwise torque. When it's over there, that would be a counterclockwise torque. So the restoring torque is mg, the weight of this object, times d sine theta. There's the moment term, d sine theta. Okay, so here's the restoring torque is equal to I times alpha. There is that. Okay, and again, for small angles, sine theta is equal to theta. So when you replace that by theta, so that becomes minus mg d theta equal to I d squared theta by dt squared. Okay. And mg d over I theta t equal to d squared theta by dt squared. And again, all these quantities are positive, so we'll call it omega squared. All right, so you get the same equation. Omega squared is mgd by I and d squared theta by dt squared plus omega squared theta t equal to 0. All right, so let me give you an example. Why do we do all of this? So here's a real life example. Okay, so since I'm recording this, so let's say here's an animal. Here's the leg of the animal. When it's walking, this is a physical pendulum. You can calculate the period of this physical pendulum. There's a point of suspension. So this could be an elephant. Okay, you can calculate the period. Okay, so to get one step, it takes half the period. So the walking speed, the normal walking speed of this animal can be calculated by calculating the period of this pendulum. Did you guys understand that? Yeah. So you can calculate the normal walking speed of a giraffe, an elephant, a rhinoceros, whatever. Yeah.
When there's like two pivots, like the knee and the hip.
Right, but when you're walking, you don't pivot around your knee. Yep, so. Yep. Anyway, it works out. They've done the calculations. So you can calculate your normal walking speed. Or you can back calculate. So you know your walking speed, you can calculate the period, and you can calculate your moment of inertia for your leg. Yeah. All right, so the period is 2 pi times I over square root of mgd. Mg is the weight of this, and d is the distance of the center of mass from the point of suspension. Do you want me to pause? Do you guys need a break, or should we keep going? Is it information overload, or you guys are good? It's a little overload, I know. All right, we'll keep the recording going, just a 30-second break, and then we'll go. All right? I don't want to start another recording. So if you have to go to the bathroom, run and come back. All you have to do is beat this guy. I think he's the fastest guy in the room. Are you the fastest guy in the room? Probably.
Unless there's some sprinters.
What's that?
Unless there's a sprinter.
No, we don't have a sprinter. Garrett, are you a sprinter?
No,
No.
long distance.
Long distance, huh?
Yeah.
What's your
When
distance?
I
Huh?
did run, I don't run anymore.
What was your distance when you ran?
When I did track, it was like mile and 2 mile.
No, see.
That's what I earned.
Sorry, what?
That's what I earned.
That's what you did too. Nice.
Okay, I know you guys are tired, but now there's not much math. Well, I mean, there is some math, but I won't go over the details. I'll just give you the punchline. Okay. Okay, this motion is called simple harmonic motion. Okay, it's simple harmonic motion if the restoring force is proportional to the displacement and the position is given by a sine or a cosine function. Okay, so if you saw that if the restoring force is proportional to the displacement, then the position is given by sine or a cosine function. And that's a simple harmonic motion. And then the period is independent of the amplitude. Okay. All right, now here's another strange thing. Well, not strange, but a surprising thing to learn the first time. If an object is going around in a circle at constant speed, this is related to simple harmonic motion. So for instance, the International Space Station going around the Earth in a circle at constant speed. So if you project its shadow, the shadow is this is a simple harmonic motion. Okay, so this is exactly like the motion of a mass attached to a spring. So uniform circular motion is a combination of two simple harmonic motions. Okay? So uniform circular motion and simple harmonic motion are related.
Isn't that like kind of like how waves work in the ocean too?
Yep,
It's a combination
they're
of-
also, yep. So the simple harmonic motion comes in, shows up everywhere. Okay, so the waves on a motion, what Gabriel is talking about is the water molecule you learn maybe in a chapter or two. They go in circles at constant speed. The surface water molecules go in circles. Okay? And that's a combination of two simple harmonic motions. Okay? As you go deeper in the water, they become ellipses. Okay, so the next few slides are showing you, okay, so here's the speed of this guy going in a circle. There's the x component, and that's equal to the velocity of the mass attached to the spring at that point. That's what this thing is showing you, okay? When you're going in a circle at constant speed, are you accelerating? Yes. You have centripetal acceleration, so there's your acceleration. And this component of the acceleration is equal to the acceleration of the mass attached to the spring. Okay? All right. Now we've graduated to the big league. Okay. What is damped oscillations?
Friction involved.
Friction involved. Okay. So without friction, here was the equation for the mass attached to the spring. Okay. With friction involved, we'll see how this equation changes. Okay. And you will see in a second, with friction involved, oops. Okay, so here's the simplest model to account for friction. With friction involved, this equation gets this additional term. Okay, so B is a measure of the friction. Okay, we'll come to that in a second. So when B is 0, this equation will reduce to the frictionless case. Okay, so this is frictionless, and this is with friction. Okay, and if you solve this equation, here's the x as a function of time looks like that. This is x as a function of time. Okay. So here's a simple way to model friction. Okay. Okay, so if this guy is oscillating in air, there is no friction, and the behavior of this guy is given by this equation. The same guy, you put it in a beaker of water. Now the behavior of this guy is given by this equation. So you guys understand? Different systems, different mathematical model. All right. So let's do this. So we're going to look at damped oscillation. We're going to add friction. And the simplest model is the friction force, the damping force is proportional to the velocity. Okay? And that makes sense. If this guy is at rest, there's no friction. Okay? And the faster it goes in a fluid, the greater the friction force. And the negative sign just tells you the damping force is in the opposite direction of the velocity. So if it's moving in this direction, the friction force is in that direction. If it's moving in that direction, the friction force is in this direction. Okay? B is called the damping coefficient. All right, again, what's our ideas? You have your system, you get a physical principle, you apply a physics law, you come up with a mathematical model, which is generally a differential equation, and then you solve solution. Yeah. So we have our very simple recipe. Okay. So here's our system. We'll apply Newton's second law, F equal to ma. Come up with the mathematical model. Okay. There's ma, there's the force. There's the spring force, and there's the friction force. Okay. Velocity is dx by dt. Acceleration is d square x by dt square. Okay. And then you bring all the terms. So here's a second order linear differential equation. Okay. None of the terms are squared. Okay. And then we will do d square x by dt square plus b over m dx by dt plus k over m x, and x is always a function of time. And this guy we called omega square, so I'm going to replace that by omega square. So here's your mathematical model with friction present. There is the friction term. So here's the equation that's describing a more complicated system. Now here's the beauty of it. Okay, if B goes to 0, there's no friction, and you get back your frictionless system. So this more complicated model contains the simpler model. The simpler model is a limit B going to 0. Okay. So it's like if you can run the 200 meters, you can certainly run 100 meters. Okay. And that's the idea. All right, again, you'll learn how to solve this. And a mixture of science and art. Yeah. So how many unknown constants are there in the solution? A and phi. That's because it was a second order differential equation. Okay? And what is happening because of the friction? Because of friction, what is happening? The oscillation is dying out. What's happening to the energy in the oscillation? It's being converted to heat. Okay, so the mechanical energy is dying out. And it turns out that it's dying out exponentially. See, the amplitude of oscillation is dying exponentially. As time increases, the amplitude decreases exponentially. Greater the friction constant, faster it's dying. Okay, greater the damping constant, faster the oscillation dies. Now, here's another change that happens. If there's no damping present, this was the frequency of oscillation. With friction present, the frequency of oscillation changes. This is omega naught square. So the new frequency is slightly smaller. It's smaller by this amount. Okay? So omega naught was the frequency of oscillation without friction. For the same system, if you add friction, now the frequency of oscillation decreases. Okay? Mm-hmm. You'll see why we care about this kind of stuff. Okay. So for instance, let's say you own a motorbike. A motorbike is the wheel is attached to the shock absorber, which is essentially a spring. Okay. Now let's say you hit a pothole. The wheel goes down. And now do you want the wheel to oscillate? Because once you come out of the pothole, you don't want the wheel bouncing. What do you want? You want the oscillations to die out fast. Okay. You don't want the wheel bouncing. You want the oscillation to die out fast. So you want to build in enough damping for the oscillations to die out. Because if there are bumps in the road and stuff like that, they'll set your wheels in oscillation, and you don't want that oscillating. So what is the damper there? Yeah, the oil and the shock absorbers. Okay? So if you make this damper large enough, if this becomes zero, then it won't oscillate at all. Okay? If this becomes larger than that, the wheel won't even come to its original spot. Again, you don't want that. So damping, a lot of times vibrations come into your life and you don't want them. So you have to kill the vibrations. And you have to have a good enough damping factor. Okay. So for instance, in large buildings, the wind will set them in oscillation. You don't want the building oscillating. Okay, so the damper there is in all these tall buildings. So one of the ways to dampen is put a large tank of water. As the building shakes, the water won't go back there. The water delays. So the building is going this way, and the water is going in the opposite direction, and the friction will damp out the motion. Okay, so in all these tall buildings, you have to have dampers. Okay. Here is another place where you have to have dampers. Okay. You drive over a bridge. The winds will set the bridges to oscillating, and you want dampers. Okay. Okay. Now we'll study an important thing called resonance. Okay. Okay, so we'll study something called forced oscillation. Okay. So every system has a natural frequency of oscillation. Okay. So for instance, you get a child to swing on a swing, that system has a natural frequency of oscillation. Now if you push the child, you're forcing the oscillation. Okay. So we'll look at forced oscillations. Do you guys understand what I'm saying? All right, so here's the equation. Mass times acceleration is the total force. Here's the spring force. What is this guy? That's the friction force. And here's the driving force. You're pushing. Okay, so here's the driving frequency. Okay. All right, again, we're not going through the details. Okay. You can solve this, and here's the solution you get. You get the amplitude is a function of the driving frequency and the natural frequency of oscillation. Okay? And the system oscillates at the driver frequency. Okay? So if the system's frequency is, let's say, the natural frequency is 50 hertz, but you're driving at 70 hertz, the system is oscillating at 70 hertz. Okay. All right, so what this graph is showing you is, it's showing you this amplitude. And tell me what you see in this graph. Okay, so what this is plotting is the driving frequency divided by the natural frequency. Okay. And at 1, what is happening? The amplitude is increasing tremendously. When the driving frequency matches a natural frequency, then you can set up large amplitude oscillations. What does this mean? Okay, so this is called resonance. When driving frequency matches the natural frequency, you can set up large amplitude oscillations. Let me show you. I'll show you a couple of simulations. Okay, so you want to see this. So what we're going to do is we're going to hold on to the spring. The mass attached to the spring has a natural frequency, and the natural frequency is omega naught. And what we're going to do is hold on to the spring and pump energy. We're going to drive like that. Okay? So right now, see, the driving frequency is that, and that's the natural frequency. Okay, so we will drive it at a frequency that doesn't match the natural frequency. Okay. No, it's too slow. Okay, so there's the driving frequency and there's the natural frequency. Okay, watch this now. So now what I've done, the driving frequency is close to the natural frequency. Okay. Now I'm going to start this. I'm going to, again, my pumping amplitude is still the same. This is scary shit. So imagine if this is the ground shaking, the frequency of the ground shaking matches the natural frequency of a building, the building will collapse. All right, this stuff is not funny. It's this stuff is real. So this was in 1985 in Mexico. An earthquake happened 255 miles from Mexico City. It's like from Miami to here. Okay, and so the ground was shaking. And this frequency matched the natural frequency of these building heights. The frequency of oscillation of a building depends on the height. It matched the frequency of this building. It didn't match the frequency of this or this. So these guys collapsed. These guys stayed standing. All right. I'm going to show you one more video because if you in a physics class you have to see this video. All right, so this was you guys might have heard of this. This was the Tacoma's Narrows Bridge. So this was near Seattle. So here's an aerial view. This is the bridge that was built. And here are the piers. So we're looking at the top view. Okay. So wind was blowing like that. That was the driver. Okay. Vortices will build up behind the piers, and they would break away at a certain frequency. That was the driving frequency. Okay, so it's like hitting this table at a certain frequency. And when this thing matched the natural frequency of the bridge, it set up large amplitude oscillations. Okay, did you guys understand that? Okay, I'm going to show you the videos. I don't want you to sleep tonight. So go become a civil engineer, and that should be your nightmare. All right, I don't want it. How many of you have seen this video before? Okay, nobody, good. bridge collapsed within a year of being built. So this was in the 1930s or so. And it still happens. Apparently they built a walking bridge in London maybe 10 years ago or something like that, less than 10 years ago. And the first day, about 3,000 people or 3,000 people were walking and it started swaying. That to close it down, 14 million was the original cost. Putting dampers, the right dampers and stuff like that was another 4 million bucks. So this stuff happens. Okay. So there's a bridge in. Okay, there's a bridge in Russia somewhere. I forget its name, but when the wind blows hard, the bridge vibrates and they have to stop traffic till the vibrations die down. Okay. And you can find the videos. So I don't know what the thing is called, but anyway. All right, guys. So
At Johnson & Johnson, we're leading the way across the full spectrum of healthcare solutions by innovating at the intersection of biology and technology. We profoundly
resonance is when the driving frequency, so an external source, so for instance, you pushing a child on a swing, when the driving frequency matches a natural frequency, then you can set up large amplitude oscillation. So what's happening is, with damping present, oscillations are dying out. But if, let's say, 10 joules of energy is being bled out per oscillation, and you pump in 11 joules of energy per oscillations, you're building up the energy. Okay? And you can set up large amplitude oscillations. Okay. All right, here are some videos. I urge you guys to go see them. So resonance is, what does resonance mean? When the driving frequency matches the natural frequency. You're setting up large amplitude oscillations. Okay. All right, and so this is a real concern in a bunch of our structures. Any tall structure, you have to have damping in place to make sure that when natural forces apply a frequency that matches a natural frequency, you don't set up large amplitude oscillations. Okay? All right. So the Burj Khalifa sways about 2 meters at the very top. 2 meters is from here to there. Okay, and try selling this property, which is the most expensive property, to somebody where the top floor is swaying 2 meters. What? And for them not to feel it.